Hello, everyone. I'm Kazutoshi Tanaka from Scenic X. Today, I'd like to talk about our novel learning method for robotic contact juggling. This slide shows the outline of this presentation. I've divided the presentation into motivation, method, and experiment. First, I'd like to talk about our motivation. This slide shows pictures of a robot playing juggling. Robotic juggling has been a fascinating task for the robotics community. As you can see in this slide, many researchers have sought to realize various robotic juggling, such as devil sticking, toss juggling, paddle juggling, and diabolo. Robotic juggling has also been serving as a benchmark for evaluating agile and dynamic robotic manipulations. We focus on contact juggling in this study. What is contact juggling? This slide shows a video of contact juggling. This performer plays the butterfly trick of contact juggling. As you can see in this video, in contact juggling, he stops, rolls, slides, and throws an object over the surface of their body. Then, he keeps the object in and sometimes out of contact with his body, without holding it in his hand. How does a robot play contact juggling? Researchers proposed methods for robotic contact juggling. This slide explains related works of robotic contact juggling. Lynch et al. Modeled the butterfly trick of contact juggling to investigate the importance of the shape of a robot. As you can see in the top figures, they developed a simple robot with one motor. This robot successfully performed the butterfly contact juggling trick using a controller based on their model. Woodruff et al. Presented a general formulation and solution for the case of an arbitrary smooth object in a single-point rolling contact on an arbitrary smooth hand. This solution is applicable to robotic contact juggling. As you can see in the bottom figures, they demonstrated robotic contact juggling using their model and a simple robotic arm in a 2D space. It is laborious to build a controller manually. How can a robot make this controller automatically? Using machine learning techniques is an answer. We are interested in a method of learning to play contact juggling from trial and error. This method does not need laborious physical modeling of complicated robot-ball interactions. Specifically, we seek an approach based on model-based reinforcement learning. Model-based reinforcement learning is suitable for robot applications owing to sample efficiency because contact juggling involves manipulations with rapid acceleration that amplify the safety requirement. But, modeling the robot-ball interactions is non-trivial, primarily because the robot must control the movement of an object indirectly by changing the position and orientation of the link over which the ball moves. So, we propose a novel model-based reinforcement learning method. This slide shows the main concept of our method. That is behavior primitives. The main concept has 2 points. First, we expect that the complex behavior of contact juggling can be divided into multiple simple behavior primitives, as you can see in this figure. These primitives may depend on whether or not the ball is in contact with the body of the performer. Second, we also expect that it is easy to model the state transition of these simple behavior. That is, a robot may learn the dynamics models through a handful of trial and error. Based on the concept, our method discovers these primitives and learns dynamics models of the primitives automatically. Our method reduces the effort for defining multiple dynamics models based on heuristics. Next, let me introduce our method. Our method is model-based reinforcement learning. That is one learning method. I'll explain model-based reinforcement learning using this slide. Model-based reinforcement learning uses a model. This model approximates the state transition dynamics. The model is learned using samples collected from the environment. The model predicts sequences of state from sequences of actions. Based on this prediction, the optimal action is selected. This slide shows the main concept of our method again. We expect that the complex behavior of contact juggling can be divided into multiple simple behavior primitives. We also expect that it is easy to model the state transition of these simple behavior. This slide introduces our method. The method is named Switched Multiple Model-Based Reinforcement Learning. As shown in this figure, the method has dynamics models and a switching model. Each dynamics model corresponds to each behavior primitives. This switching model G selects a proper dynamics model from the current state and action. The method selects optimal actions using model predictive control with prediction using the dynamics models and the switching model and episodes. How does the method learn these models? One goal of the model construction is building dynamics models from collected samples in the database. As you can see in this slide, collected samples are ones when all states and actions during trials of contact juggling. And each dynamics model represents each behavior primitive. So, our method divides samples into subdatabases based on features of samples. Each subdatabase corresponds to each dynamics model. The method attaches labels in each subdatabase and builds the switching model using these labels in subdatabase as a classifier. After each episode, the method constructs models. The database has collected samples. At first, all samples are extracted. Second, extracted samples are fit to a simple function. The maximum fitting error is calculated. Third, if the maximum error is smaller than a value, the extracted samples are added as a new subdatabase, and the fitted function is added as a new dynamics model. Fourth, if the maximum error is larger than a value, the maximum error sample is removed and added to the database. Fifth, a random sample is extracted every some steps. This is for avoiding a local minimal solution. If the number of the extracted samples is smaller than a value, constructing dynamics models is ended. After these procedures, the method attaches labels in each subdatabase and builds the switching model using these labels in subdatabase as a classifier. Lastly, I'll explain our experiment. To verify our method, we implemented a realistic 3D simulation of contact juggling environments using the Gazebo robot simulator. We simulated motions with a 25 Hz control cycle using a 0.001 second time step. As you can see in the figure, we used a model of a robotic arm equipped with a flat hand and a ball model of 0.05 meters radius and 0.45 kilograms weight. The robot cannot hold this ball with its flat hand. Thus, the robot indirectly controlled the movement of the ball by changing the position and orientation of the hand. As you can see in this slide, the state contains the position and the orientation of the hand and the position of the ball. The action is the target angular velocity of all joints of the robot. The reward quantifies the squared error of the current state to the optimal state at each time point. The optimal state was defined as the target trajectory that we empirically designed. To evaluate the effectiveness of MBRL for training a robot to perform contact juggling, we calculated the mean, median, and standard deviation of episodic returns when learning the task. The robot learned contact juggling in 20 training episodes. The robot learned to throw the ball in 0.4 seconds in the first 10 episodes and learned to execute throwing and catching the ball in 1.0 seconds in the next 10 episodes. To verify our method, we compared our method with 3 baseline methods. Baseline 1 uses one complex dynamics model, while our model uses multiple simple dynamics models. We compared our method with this model to investigate the effects of using multiple models. Baseline 2 uses multiple simple dynamics models, trains these models using a backpropagation method, and calculates the outputs by the linear combination of dynamics models. We compared our method with this model to investigate the effects of selecting proper dynamics models and the effects of using a least square method. Baseline 3 is our method without random extraction. This slide explains the random extraction again. A random sample is extracted every some steps. This is for avoiding to a local minimal solution. We compared our method with this method, baseline 3, to investigate the effects of the random extraction. This video shows a robot that is learning contact juggling using our method. As you can see in this video, the robot successfully learned contact juggling using our method. This video is slow motion. This video is real time. This slide shows the episodic returns of our method and the baseline 1. Baseline 1 uses one complex dynamics model, while our method uses multiple simple dynamics models. To verify the effects of using multiple models, the returns of our method and ones of baseline 1 were compared. As you can see in figure, the medians of the returns during the first episodes of learning throwing were larger when using baseline 1 than our method. We confirmed that our method improved the median of the returns during the first episodes of learning throwing and catching the ball compared to baseline 1. These results suggest that the robot learned the throwing and catching actions faster using MBRL than baseline 1. This may be because of the simplicity of each dynamics model in our method, which requires fewer samples than complex models such as those used by baseline 1. To confirm that MBRL divides samples into subdatasets based on the primitives in contact juggling, the positions of the ball and the samples were plotted in this figure. The classes of the positions were predicted by the learned switching model from collected all samples after all episodes. As you can see in the figure, interestingly, the positions corresponding to the time when the ball was in the air belonged to class 1, and other samples corresponding to the hand touching the ball belonged to class 2. This result suggests that the switching model learns to select models corresponding to different contact conditions. To verify the effects of using a switching model and the effects of the random tuple extraction, the returns of our method, ones of baseline 2, and ones of baseline 3 were compared. As shown in this slide, the median values of the returns of baseline 3 and our method for learning throwing were very similar. We confirmed that our method improved the median during the first few episodes of learning to throw and catch the ball compared to baseline 2 and baseline 3. These results indicate that selecting a model and the random extraction in our method is fundamental for a robot using multiple dynamics models to learn contact juggling. Let me summarize this presentation. We developed MBRL, a novel MBRL method tailored to learning robotic contact juggling. We confirmed the effectiveness of the proposed method via realistic simulations of a robot learning contact juggling. In the simulations, a robot arm using MBRL moved and stopped a ball based on the target trajectory. Thus, MBRL will also enable a robot to perform more complex contact juggling tricks based on another target trajectory. We are going to apply MBRL to other robotic contact juggling and practical tasks such as peg and holes. That's it. Thank you for listening.